A lone crane, towering like a sentry, gradually spins a massive wheel overhead. As it turns, a single strand of steel uncoils from a towering spool and begins to twist itself into place, a beautifully choreographed dance of engineering and gravity. This steel wire, deceptively slender, will join with thousands of its brethren to form the main cable of a suspension bridge. Yet, there is a quiet tension in the air. The site is buzzing with activity, but there remains a question that lingers like the fog above San Francisco Bay, blanketing the Golden Gate Bridge. Why, when constructing these engineering marvels, do engineers choose to spin the cables in place rather than pre-make them elsewhere? It is an intriguing puzzle. Imagine a machine capable of supporting hundreds of thousands of tons, spanning immense distances. Yet, the very cables that hold it together are created in situ, not manufactured in a factory or on a distant floor. This raises the stakes. If pre-made cables are the apparent solution, why are they not the norm? As we delve deeper, we promise to uncover the surprising truth behind this unconventional approach, laying bare the physics and practicalities of this fascinating method. To grasp why suspension bridge cables are spun on site, we must first understand the basic mechanics behind their construction. One of the defining features of a suspension bridge, such as the iconic Golden Gate, is its main cables, which support the weight of the bridge deck and any traffic above. A single main cable can consist of over 27,000 individual wires, each no thicker than a finger. That adds up to a staggering capacity of strength, but a challenge remains: how do you transport a finished cable that is hundreds of feet long and weighs thousands of tons? As we look into this phenomenon, we find ourselves confronted with a problem of scale and logistics. Consider this: the main cables of the Golden Gate Bridge span roughly 4,200 feet in length. If a factory were to try to assemble these cables in a pre-made format, they would require an equally massive and specialized transportation vessel, one capable of handling something the size of a football field that can weigh as much as 200 tons. This is where the engineering constraints begin to emerge. Such vessels are scarce, and their expenses are exorbitant. The sheer logistics of transporting a pre-made cable of that length and weight would be a monumental challenge, often making it a practical impossibility. Hence, engineers turn their focus to a more innovative solution: spinning the cables on site using a carefully calculated process. To understand how this works, we need to investigate the mechanics of aerial spinning. Engineers utilize a technique called cable spinning. A tensioned wire is pulled from a large spool through a series of spinning wheels that rotate around a vertical axis above the bridge. With precision, these wheels guide the wire into place, twisting and layering it around a central core. Imagine the intricate dance of a spider weaving its web. Each strand must be holistically interconnected to create a structure that is strong yet flexible. The engineering behind this process is no less elaborate. The cables are created under controlled tensions, ensuring each wire is tightened to exact specifications, which regulates the load and distributes stress evenly throughout the structure. The primary strength derived from this method lies not only in the materials used but in the deliberate layering of each wire within the cable. Let's take a closer look at the remarkable quantities involved. Each wire used in the Golden Gate Bridge's main cables is approximately 1/4 inch in diameter. When considered together, they create an astonishing total diameter of around 36 inches for the finished main cables. That's a cable whose stability derives from the collective strength of thousands of individual strands. Upon initial examination, one might think that transporting a prefabricated cable would be much simpler and efficient, allowing for quicker assembly on site. However, that assumption overlooks one crucial aspect: the reality of manufacturing tolerance. When wires are assembled off-site, they must be created to very precise specifications to ensure proper functionality. Any minuscule error introduced during this phase may contribute to significant problems once the cables are actually installed. In effect, prefabrication requires adherence to stricter manufacturing tolerances that can compound issues over vast distances. Bridge engineers, hence, rely on the spinning process not only for logistical reasons but also to maintain control over the delicate balance of strength and flexibility during construction. But what happens if the engineering philosophy is reversed? Consider the Tacoma Narrows Bridge collapse of 1940. Prefabricated cables were used, resulting in unexpected aerodynamic problems that led to the bridge's failure. The shifting load dynamics and structural vibrations caused by wind led to catastrophic failure, a stark reminder of the importance of bespoke engineering tailored to specific environmental conditions. Now, inspired by the marriage of science and artistry, we know that spinning cables in place brings several benefits. It provides the chance for real-time adjustments, enabling engineers to dynamically respond to environmental variables and mitigate unforeseen issues immediately. An in-situ assembly method also provides a significant advantage in ensuring quality control. Let's pause for a moment and consider a pertinent question. Which of these machines would you least want to be standing next to? A colossal crane lifting massive steel beams? A spinning mechanism generating mechanical forces that can crush hundreds of thousands of pounds? Or perhaps a far-reaching suspension bridge still under construction? It's essential to be cognizant of operational safety around these engineering marvels, especially during their assembly. Yet, putting aside the inherent dangers, what often surprises is the misunderstanding of cable winding itself. People often assume that spinning cables would be inefficient or prone to breakage when subjected to high loads. In reality, the opposite is true. Here's the actual trick: spinning them in place allows for a unique control of each wire's tension, facilitating the creation of a composite structure that can adapt under stress. Rather than seeing individual wires as weaker elements, they become integral components of a greater engineered solution that is stronger than the sum of its parts. Returning to the subject of scale, let us reflect on the enormous impact of this choice. Projects like the Golden Gate Bridge, which took about 4 years to complete, or the Mackinac Bridge, stretching over 3 miles, relied on this largely unobserved engineering method. The sheer scale of these structures forces a quiet respect for the ingenuity behind their construction. There is a level of artistry involved in engineering that often goes unnoticed. The reality is that these structures embody not only advanced principles of physics and materials science but also reflect the ingenuity and resolve of human creativity. So the next time you stand below a grand suspension bridge, take a moment to consider the countless hours of design and construction that went into it. Look at its cables, not as mere objects but as carefully orchestrated strands of steel that hold together an extraordinary feat of engineering ingenuity. Every giant machine hides one piece of engineering nobody notices. Subscribe for the next one, and tell me below which machine you want taken apart. To further unravel the intricacies of spinning suspension bridge cables in situ, it is essential to delve deeper into the mechanics and the historical instances that shaped this approach. Beyond the immediate reasons of practicality and control, engineers also account for an element known as sag, a critical factor in the design of suspension bridges. When a cable is suspended from 2 towers, gravity exerts a significant force, compelling each wire to bow slightly under the weight it carries. The resultant shape is known as a catenary curve. This curve is not merely an aesthetic feature, it is an essential element that influences the distribution of forces throughout the bridge. Pre-made cables, if assembled incorrectly, can introduce an imbalance in this curvature, leading to catastrophic miscalculations in stress distribution. A vivid illustration of this principle can be found in the construction of the Chesapeake Bay Bridge, completed in 1964. This bridge spans over 4 miles and demonstrates a keen understanding of the interplay between tension, sag, and load. Engineers used the in-situ spinning method to ensure that the main cables maintained the appropriate catenary shape, allowing them to strategically distribute the weight of the roadway and the forces coming from traffic above. By spinning the cables on-site, they could easily visualize and immediately correct any discrepancies that might arise during construction. The need for ongoing adjustments while spinning the cables also ties directly into what is known in engineering as live load. Live load refers to the dynamic weight applied to the bridge, such as vehicles, pedestrians, and even environmental factors like wind and seismic activity. The spinning cables were carefully calibrated to withstand these loads dynamically, unlike prefabricated cables, which could lead to a rigid structure that might not flex adequately under varying conditions. Consider the example of the San Francisco-Oakland Bay Bridge, which encountered both a major earthquake in 1989 and the subsequent renovations that addressed the vulnerabilities exposed during that tremor. The extensive reinforcement work that followed showcased that engineers had not only to account for static forces but also for dynamic responses in their designs. Having the ability to spin cables on-site meant that they could implement real-time modifications based on the bridge's behavior under such unpredictable stressors. This sense of adaptability is a cornerstone of contemporary civil engineering. Projects like the new Gordie Howe International Bridge, set to connect Detroit and Windsor, reject the notion that prefabrication is the only or even the best way to build. The spinning of cables directly correlates with modern engineering advances that prioritize flexibility and resilience in infrastructure. At the core of spinning cables lies another layer of complexity: wave propagation. When a load is applied to a suspension bridge, stress waves travel through the main cables at considerable speed. Cables that are spun on-site can be engineered to dampen these stress waves more effectively than those made off-site. A pre-made cable is essentially a fixed unit, which may transmit these waves uniformly, ultimately affecting stability. Conversely, in-situ spun cables have been shown to manage these forces better and provide a significantly lower risk of resonance, a phenomenon that can lead to structural failure. A case study that emphasizes the importance of this principle occurred in the construction of the Millau Viaduct in France, completed in 2004. This extraordinary bridge, soaring over 1,161 feet above the Tarn River, is an architectural marvel. The design required careful attention to shock wave behavior, especially during heavy wind conditions. Engineers chose to employ tension cables spun directly on-site to optimize the bridge's capacity to respond to these forces, affording both safety and performance benefits. The narrative surrounding cable spinning extends beyond mere technicalities. There's an inherent artistry in harnessing the interplay of physics and creativity to create something as awe-inspiring as a suspension bridge. Every twist, every layer of wire spun into the cables represents a decision informed by an understanding of both the environment the bridge will face and the loads it will carry. Furthermore, let's venture into the realm of cable materials. Historically, steel has been the primary choice for main bridge cables due to its tensile strength and versatility. However, with innovations in materials science, we've witnessed the introduction of alternative materials such as carbon fiber and synthetic fibers in less conventional applications. While these materials have yet to replace steel in major suspension bridges, engineers are keen to explore their potential, especially in hybrid designs. Another fascinating chapter in this narrative arises with the notion of maintenance. Spun cables not only provide the initial strength necessary for support but also allow for more straightforward inspection measures. In-situ assembly enables engineers to weave in sensors directly into the wires during installation. This technology allows for continuous monitoring of tension levels, degradation due to environmental factors, and material fatigue over time, ensuring proactive maintenance rather than reactive solutions, which can be both costly and dangerous. Reflecting on the legacy of in-situ cable spinning, we cannot ignore the impact on safety protocols. The tradition of the bridge engineer, a mix of physicist, artist, and a risk manager, has transformed significantly in response to events like the Tacoma Narrows Bridge collapse. Every cable spun on-site carries not only the weight of the physical structure above but also a long history of lessons learned in engineering. Another aspect worth noting is public engagement. As societies worldwide invest in infrastructure, educating communities about the engineering principles behind these giant machines fosters appreciation and respect for the advancements in civil engineering. The transparency of processes such as spinning cables on-site captivates interest and enriches public knowledge about the sophisticated work that supports their daily journeys across these colossal structures. At the end of the day, every strand spun into place represents more than just an engineering feat. It embodies an ethos of striving for innovation, safety, and resilience. As we continue to face challenges posed by climate change, urbanization, and increased traffic demands, the lessons derived from the spinning of cables are crucial. They teach us about adaptability and the importance of grounding technological advancements in sound engineering principles. As we conclude, the world of suspension bridge engineering continues to evolve, but the meticulous craft of spinning cables in place stands as a pivotal practice. It represents a thoughtful acknowledgement of the forces at play and the engineering challenges that lie ahead. The next time you cross over a grand suspension bridge, an architectural achievement rising above the landscape, remember the marvel of its cables, spun in real time, woven into the fabric of the structure, and engineered to hold the weight of innovation and necessity alike. Every giant machine hides one piece of engineering nobody noticed.